Okay, welcome guys to Physics 203 Class 20. This class is on quantum numbers. These are the discrete integers we use to specify the states of quantum systems. And for the one-dimensional square well, which we've studied previously, there was one quantum number n, which corresponded to the energy of the particle in the infinite square well. And there was one quantum number because that system was one-dimensional. Here we're going to be looking at the quantum numbers for the hydrogen atom, and there are three of those, as we saw in the previous class. And we're going to be looking at the rules that these quantum numbers have to satisfy. There's some relations, they depend on one another. And also at what each quantum number means physically. And finally, we'll look at a naming system, a system of nomenclature for the quantum states of the hydrogen atom, and also look at what physical quantities in terms of energy and angular momentum we can know simultaneously in accordance with the uncertainty principle. So, hydrogen quantum numbers, the origin and the rules, we'll see in a second. The origin, so remember we separated variables when we solved for the time-independent Schrodinger equation for the hydrogen atom, and we had a function of r alone, a function of theta alone, and a function of phi alone in spherical coordinates. And those functions were determined by the radial equation here, by the angular equation here, and by the azimuthal equation here. And the two of the quantum numbers appear here. L is a quantum number, and m sub L is a quantum number, and the third quantum number n is associated with the radial equation here. So in solving the radial and angular equations with boundary conditions and necessary properties for the wave function, like the fact that the wave function has to be single valued, which gave us only certain allowed values for m sub L, you might remember, we find there are restrictions on the values of these quantum numbers. So they, in general, they can take on integer values, but depending on the value of the quantum number n, L can only take on certain allowed values, and depending on the value of the quantum number L, m sub L can take on only certain allowed values. So this is the result of solving these equations and applying the boundary conditions that the radial function has to go to 0 at infinity, and the angular equation is the angular function is single valued, and several other restrictions. So n, which is the radial quantum number, or also called the principal quantum number, can be any integer 1, 2, 3, 4, and so forth. L runs from 0 up to n minus 1. So, okay, and we'll see an example of this in a second. Meanwhile, m sub L can run from minus L all the way up through 0 up through plus L. Okay, so again, all of these are integers, but depending on what value n has, that determines the possible values of L, which in turn determine the possible values of m sub L. So just to take an example, if we pick n equal to 2, we have, according to this, L equals 0 up to n minus 1, which would be 2 minus 1 or 1. So we must have L equal 1 or L equals 0 or L equal 1. For L equals 0, we must have m sub L runs from minus L, which is 0, to plus L, which is 0. So it's just, we must have ml equals 0. Meanwhile, for L equal 1, we can have M sub L equal -1, that is minus L, 0, or 1. Okay, so so we have 4 states in total for n equal 2, and written as a triplet of the quantum numbers m, n, l, and m sub l. They would be 1. Sorry, this should be 2. 2, 0, 0. Okay, 2, 0, 0. 2, 1, -1. 2, n equal 2, L equal 1, ML equals 0, 2, 1, 0, and 2, 1, 1. Okay. So again, this is a misprint. This 1 should be a 2. So it should be 2, 0, 0 here. Okay. So great. So what's the physical meaning of these quantum numbers? How can we interpret them? How do they connect to physical quantities? The principal quantum number n, or the radial quantum number, determines the energy through this formula, which comes out of the solution of the radial equation. And it turns out that the energy is equal to minus a constant, all these fundamental constants, over n squared. And this combination of constants is actually the Rydberg constant, E naught, which is 13.6 eV. So this actually matches the Bohr model, which is satisfying because the Bohr model predicted the energy differences, the photon energies, and the wavelengths of the hydrogen atom. So we'd hope that the energies matched up. The angular quantum number L determines the angular momentum. So angular quantum number, angular momentum. And the allowed values of L turn out to have a little bit of a funny form. The allowed values of capital L, the angular momentum, are the square root of the quantum number L times L plus 1, all of that square root, times h bar. Okay, and we'll give a brief argument in a second for why this formula should hold. This funny looking formula should hold. But notice that in the Bohr model, Bohr assumed that L was equal to an integer, which he called n, to be distinguished from this principal quantum number n, times h bar. So this replaces and makes more accurate the Bohr result. This is an actual more accurate result. Finally, the magnetic quantum number m sub L determines the component of angular momentum along the direction of measurement. So a hydrogen atom sitting in empty space doesn't have any preferred direction to it, any preferred direction in space. But if something comes along and measures the angular momentum along a certain axis, the magnetic quantum number m sub L is involved in determining the possible values for the angular momentum along projected along that direction of measurement. And that turns out to be, that direction of measurement is usually referred to as z, the z-axis, and Lz is just equal to the third quantum number, ml, the magnetic quantum number, times h bar. Okay, and we can see the relationship between L, the total angular momentum, and Lz here. This is this diagram is for little l, or lowercase l, equal to 2. So that would be 2 times 2 plus 1, or 2 times 3, or 6. So the length of the angular momentum would be √6 times h bar. And we can see that m sub L can be either, can run from -2 h bar all the way up to 2 h bar, okay, because lowercase l is equal to 2, so it runs from -2 up to +2. And so this leads to what's called space quantization, because with a fixed length of the L vector, there are only certain directions in space which, when projected onto the z, or the measurement axis, will give integer values multiples of h bar. So there's only certain directions in space that the angular momentum can point when a measurement is made. And also notice that it's not possible for the angular momentum to point along the direction of measurement, okay, because that would lead to uh, uh, an ML value of, say, 3, but 3 is greater than the square root of 6. So it must, the angular momentum can't point directly along the direction of measurement. It has to point either perpendicular or some angle in between, but not at 90 degrees. Okay, and so here's the argument for the unusual form of the angular quantum number here, the L square root of L times L plus 1. So for a given value of L, a lowercase l, there are 2L plus 1 allowed values of M sub L. Okay, that's because according to the rule, M sub L runs from minus L up to L, including 0. So there would be L values below 0, L values above 0, and then adding 0, that's 2L plus 1. Now, the angular momentum L is a vector, so we can write, according to the Pythagorean theorem, L squared is Lx squared plus Ly squared plus Lz squared. Okay, that makes sense. Just like in spherical coordinates, r squared is x squared plus y squared plus z squared. This is just saying that L is a vector. But as we say that there's no preferred direction in space, so we expect the expected value, the expectation value of Lx squared, Ly squared, and Lz squared to be equal, because there's nothing to pick out. There's nothing to pick out x or y or z for say a hydrogen atom just sitting in space. And so then we can say that the expectation value of L squared would be the sum of the expectation values of Lx squared, Ly squared, and Lz squared, but they're all equal. So each of these is equal to Lz squared. So we can say that this is just equal to 3 times the average value of Lz squared. Well, to find the average value of Lz squared, we would take Lz, square it, sum over all possible values of M sub L. So that gives a sum of M sub L equal minus L to L of ML squared H bar squared here. And then divide by to get an average value, which is what the expectation value is, we would divide by 2L plus 1, which is what we said are the total number of allowed values for M sub L. Okay? And then evaluating this sum from minus L to L of ML squared, that's a known from discrete math. It turns out that, well, you can see the H bar squared here, but it turns out that the expectation value of L squared is L times L plus 1. Therefore, L itself, the length of L, would be the square root of L times L plus 1. Okay, so that's where that kind of funny expression comes from. Okay, so we're almost done here. I want to go over the naming system for wave functions. This started from the early days of spectroscopy. The L equals 0, 1, 2, 3, 4, 5 states have letters associated with them. And the letters for the L quantum number are S, P, D, F, and then after F, it goes up alphabetically G, H, I, J, etc. But we rarely deal with anything greater than G, maybe occasionally H. But S stands for sharp, P stands for principal, D stands for diffuse, and F stands for fundamental. And this had something to do with properties of these states observed by early spectroscopists. So if we have a pair of quantum numbers for the hydrogen atom, an NL pair, it's specified in this notation by the radial quantum number, or the principal quantum number n, followed by the appropriate letter for the L. So for example, n equal 2 and L equal 1 would be written as 2 for the n equal 2, and then L equal 1 we would look up in this table here and find P. So this state is referred to as a 2P state. Okay, so this is used in physics, but especially in chemistry and study of orbitals. Okay, and then finally, suppose we know uh, N and L sub Z, and through N we know the energy as well. Is it possible for us to know another component, another of the components, Lx or Ly, the other components of Lz, of L rather, the vector L? This is the magnitude of the vector, not the vector itself. The answer is no, but why would this be? And it has to do with the uncertainty principle. So if we know the length of L and Lz, then if we knew Lx, the x component, that would give us knowledge of Ly also, because we have this relationship L squared is equal to Lx squared plus Ly squared plus Lz squared. So if we know Lz and we know L and we're given Lx, we can solve for Ly. So we would know Lx, Ly, and Lz. So we would know the full vector L. Now, for angular momentum, the motion of the electron would then be confined in a plane perpendicular to the vector L, okay? Because L is equal to R, classically equal to R cross P. So the radius, the location of the vector has to be perpendicular to this vector L. So here's L. Let's say it just points up. It could point in any direction, but the motion of the electron would have to be confined to this plane here. It would be, some kind of motion confined to that plane, perpendicular to L. But then we would know the position along this direction with zero uncertainty. It would have to be right in that plane. And also, because it can't move out of that plane, there must be zero linear momentum. So we would know the linear momentum along that direction with no uncertainty as well. So the position of the momentum along this, in this case, is drawn or made a figure of the z direction, would each have zero uncertainty. And this violates the uncertainty principle that the product of the uncertainty of position and the uncertainty of momentum must be greater than h bar over 2. Okay, so in this lecture, we've looked at the quantum numbers n, l, and m sub l. We've seen that there are rules for what values they can take. We've looked at their physical interpretation in terms of energy, angular momentum, and the component of angular momentum along a certain axis. And we've determined that it's possible only to know certainly the magnitude of the angular momentum, the energy, the magnitude of the angular momentum, and one other component of the angular momentum. All right, thanks for your attention, and I'll see you in class.